Welcome back. So in the previous part of the 16th lecture, we established that beta 1 will represent a causal impact of the number of rooms on the price that is realized in the market for a particular home. That is, the causal impact of Ri on Pi is given by beta 1 if we have a crucial assumption A2 satisfied, which means expectation Ui given Ri is 0. This means that whatever the value of Ri, be it Ri equals 1, that is it's a 1 room home, it's a 2 rooms home, it's a 3 rooms home, 4 rooms, and so on and so forth, the expectation of Ui will remain exactly the same if I were to change the level of Ri, right? And in fact, the expectation of Ui will not only remain constant, but it will also be equal to 0. That is the scope of assumption 2. Now, this basically implies that when Ri changes to Ri plus 1, all else is held constant. Everything that is observable and unobserved in Ui is all held constant. That is why beta 1 in the regression model equals del Pi by del Ri, which implicitly assumes, right, this partial differential notation implicitly assumes that all else was held constant. Now, if this was a deterministic equation, if we only worked with yi equals beta 0 plus beta 1 Ri, this formulation, mathematical formulation that del Pi by del Ri will automatically suggest that all else is held constant, right? Now, what does it mean to say that all else is held constant? It means that if I change Ri to Ri plus 1, the factor sitting in front of beta 0 still remains 1. So, whatever change I see in yi is going to come from the change in Ri, right? And this can be true even if I had, let's say, beta 2 x2i, right? I had another covariate x2i. The formulation that beta 1 equals del yi or del Pi over del Ri will implicitly, automatically hold xi value to its original xi. It doesn't let it move from there. That's what beta 1 measures in a deterministic equation. The trouble is that in a regression, we have this random term, this random draw coming out apart from all the deterministic variables. And the only way to be able to, hold the Ui value constant when we change Ri from Ri to Ri plus 1 is this assumption A2, right? That is why it is perhaps the most crucial assumption of a regression equation, because it ensures, causal impact of Ri on yi being represented as Pi here, right? Now say for example, Ui comprises of an index for public amenities, in the neighborhood of house I, right? Now, I'm going to sort of use a mathematical notation for these public amenities as AI, such that correlation of Ri and AI is non-zero. In fact, I'm going to go one step forward and say, in fact, I'm going to say Ri and AI are positively correlated. That is to say that if you have better amenities in a neighborhood, you're likely to find larger homes in that area. That's kind of a posh, community understanding in the Indian society, right? Or any real estate market. Typically, if you have lots of, public parks surrounding a very good sanitation infrastructure, good roads, the crime rates are under control, there is a lot of security arrangements. Those are the communities which typically have larger homes and not, one-bedroom condos, right? And in areas which are dense and you have less public amenities, people living in less secure conditions. Yeah, the quality of roads are poor. You find smaller one bedroom apartments in a city like New Delhi or in general in India, right? So smaller homes, or smaller number of rooms, if that is the index for space, is found in areas where the index for amenities is lower, right? Now with that understanding, you can say that this will imply that correlation of Ri and Ui is also by extension equal to 0, because AI is in UI. It is not controlled for explicitly. We don't have a measure of it. Just because we do not measure AI doesn't mean it doesn't affect PI. It affects it because I cannot measure it and I cannot control for it in my regression equation. As an analyst, it sits in the error term UI. Okay. Now, I've talked about the interpretation of AI. It basically says that if you have higher better public amenities, you're likely to have more spacious more spacious homes or apartments, and that would sort of provide an understanding that there are bigger apartments with more number of rooms, right? Then, if delta Ri is not equal to 0, implies delta Ai is not equal to 0, we cannot simulate what is called as a ceteris paribus experiment, wherein upon changing Ri to Ri plus 1, we could hold all else constant. So a ceteris paribus experiment is one where if I change a covariate xi, or in this case Ri, I can hold everything else constant, right? If I am not able to hold everything constant and something moves in the error term, that means expectation of Ui given Ri is non-zero, then that would imply that the impact that I see on Pi upon this marginal change in Ri is not a causal impact, but merely an association between Pi and Ri. Okay, so we have seen this formulation that if I have a change Pi tilde minus Pi, is attributable solely to Ri changing to Ri plus 1, that is delta Ri equals 1, only if correlation of Ri and Ai were 0. This implies correlation of Ri and Ui is 0, and this implies expectation of Ui given Ri is 0. Okay, these things will go both ways. So the implication is it's double implied. Now this is also the difference between correlation, or what we say association, and what is called as causation. So when we talk about spatial regression analysis, we will then interpret these items in terms of spatial dependence. So if spatial dependence interferes with expectation Ui given Xi, that's when we have a problem in terms of establishing causality in a spatial regression model. Okay, if spatial dependence sort of is the one which is correlated with one of the Xi's, then we are in trouble, right? If prices were correlated in a community, let's say they are spatially correlated in the sense that higher priced homes are clustered together and we don't control for it, right? Then that will also be an index for higher, room sized or higher, more spacious homes are clustered together. And if we don't control for such a phenomenon, then that phenomenon is sitting in my UI term, and that will start to interfere with my causal inference. And this is something we will study in a more conceptual setting, going forward. Okay. Moreover, the data-driven estimate of beta 1, that is, beta 1 hat, is unbiased only if, expectation of ui given xi is 0, right? So the regression estimator, that is the data-driven estimate of beta 1 hat, is also unbiased. That is, it is a good representation of the true, model beta 1 only if you have a expectation ui given xi equals 0. Why is that? Because look, the definition of beta 1 arises from the fact that pi or is sitting on the left hand side and ri is sitting on the right hand side. So beta 1 by definition measures a unidirectional relationship which starts at ri and ends at pi. If expectation ui given xi fails, that means the causality is not in the direction of ri to pi, rather it is merely an association which can come from pi to ri as well. So it's a circular loop where we cannot identify which direction the impact is. That is by definition merely correlation or causation, right? So if expectation ui given xi fails, then that is we cannot simulate a ceteris paribus experiment. That is we cannot establish causality, we are merely dealing with a correlation estimate. Then we might as well not go through this pain of conducting regression analysis and might just rely on a correlation, statistic correlation between pi and ri. That is sufficient. We don't need a regression, right? So everywhere and anywhere you see a regression analysis being done going forward, you should critically analyze whether or not this is a correlation or association, or it is indeed a causal impact. In social sciences, causal impacts are really important. It's kind of important because you see there is, if you think about even the real estate market, if developers or builders are building spacious homes, should they really be investing in larger space homes? You get 1 unit for a very large space versus 4 units in that equal space, which is a good deal by policy of a real estate business, right? If the premium of having a larger house does not translate into better pricing, then perhaps we shouldn't find larger homes in the market. But that's not the case, right? So this beta 1 is not merely a mathematical unit. It's a real world. It has a real world interpretation and real world implications that on which a lot of investment is riding, right? Similarly, if you have programs like the Skill India program, did it really create more jobs, right? If you do not conduct causal analysis, then your investment might not produce, it might go into waste. If you provide higher MSPs for crops, does that translate into better welfare for farmers? You need a causal inference. Correlations are not enough, and that's where social scientists and more particularly economists are focused in terms of evidence-based policy. Okay, so moving the discussion forward, we have looked at 2 assumptions till now. We will now quickly look at a few more assumptions of the regression model and end this lecture. The third assumption is that the variance of ui given xi is sigma squared, right? That is, it does not depend on I. It is a constant, but a constant which is the same for all i's. Moreover, it says covariance of ui and uj given xi is 0 for all I not equal to j. That is the variance covariance matrix for ui, right, is given as variance of u, where u is a n by 1 collection of all the error terms from 1 to n. This is going to be a n by n matrix, right? We have seen that the variance covariance matrix is a square matrix of size n by n if it is a variance covariance matrix of a n by 1 vector, where the diagonal terms are just the variance terms and the off diagonal elements are covariance terms. Right, and also it is symmetric. So, if you have covariance u1, u2, you will have a symmetric term covariance u2, u1, where it is exactly equal. It doesn't matter which order you are calculating the covariance at. So, un, u1, covariance un, u2, and keep going like this. Okay. So we have this variance covariance matrix, and for assumption 3 says that this matrix looks like the following. So all off diagonal elements are 0 and diagonal elements are exactly the same, that is sigma squared, which can be simply written as sigma squared in, right. So the variance covariance matrix is written as sigma squared in. This could also translate into, this implies that expectation of ui squared, this is the second moment of ui, is sigma squared for all I, right. This can then also be written as, so and the covariance again ui uj given xi xj is 0 for all I not equal to j. In matrix form, right, we have to always learn to translate between matrix and scalar forms, because they are very useful in terms of reading papers and textbooks, right. Mostly textbooks are written in vector form. So this module, this recap, is not only giving you a recap of the regression model, but also I hope it is giving you this translation between the scalar form and the vector form. So in the matrix form, these two conditions can be then compressed into a expectation u prime equals sigma squared in. What does that mean? Let's look at the LHS. So we have a n by 1 and a 1 by n. So I have a n by n, which is what I should be looking at. So I have an expectation operator sitting here. I have u1, u2 all the way to un, and its transpose u1, u2 all the way to un as a row vector. This, when we multiply as n by 1 and 1 by n, they are conformable. If we multiply, we get expectation of u1 squared, u1 u2 all the way to u1 un, then u2 u1, u2 squared all the way to u2 un, then you have un u1, keep going, un u2 all the way to un squared. So all the diagonal elements are squared values. So the expectation operator, being a linear operator, simply goes in and applies itself directly to each term here. So this is going to be expectation u1 squared, expectation u1 u2, keep going, expectation u1 un, expectation u2 u1, expectation u2 squared, keep going, expectation u2 un, similarly all the way to expectation un u1, expectation un u2 until expectation un squared. Okay. Now this matrix in front of you, that is expectation u prime, is nothing but the variance covariance matrix, right? Because if you look at it carefully, expectation ui squared is nothing but variance of u1, given that expectation ui is 0. Expectation u1 u2 corresponds to covariance between u1 and u2, and similarly expectation u2 u1 is corresponding to this. This will imply that expectation ui squareds directly correspond to this factor sigma squared, and expectation u1, u2s are all going to be zeros, right? That means that this matrix is nothing but, you know, sigma squared, sigma squared, sigma squared, and zeros everywhere else. This will imply that expectation ui squared, okay, given xi is 0 for all I, and expectation ui uj given xi xj will be 0, sorry, the above one is sigma squared, for all I not equal to j. These two combined are also sometimes, you know, we say errors are spherical. So the third assumption that we take is the assumption that the variance of each ui term is a constant and equal across all ui's, and the errors are not correlated. So home 1 and home 2, whatever we have not observed is not correlated by itself. Okay, this is the third assumption. Okay, let's move on to assumption 4. Okay, assumption 4 means rank of the covariate matrix X, which is, let's say, a n by k matrix, is equal to k. What is this x n by k matrix? Well, you can think of this as the x vectors arranged in columns. So my regression equation is yi equals beta 0 plus beta 1 xi, beta 2 x2i, all the way to beta k xki plus ui. Now I goes from 1 to n. That means that all these, you know, xi's are arranged in columns. So the first column is just a column of ones. How many of these are there? N of these are there. There are n rows of ones as the first covariate. The second is x1 1, x1 2, all the way to x1 n. This is the first covariate. So in case of my price and the model for house prices, the real estate market, x11 is the number of rooms in home 1 or house 1. x12 is number of rooms in house 2. We have data for it. Say we have more data, let's say, you know, the size of the kitchen, I don't know, right? That might be the second covariate, x211, x222, x22, and x2n. Similarly, we have xk1, the kth covariate. The kth covariate would be the crime rate near to that house, in the neighborhood of that house. xk1, xk2, all the way till xkn. These are all, this is the entire data that is included on the right hand side of the model. Okay, when we say that this has the rank x, what we are really saying is that, you know, all columns of x n by k are linearly independent. That is to say that, you know, because I have, you know, I do not have superficial data. If I have, let's say, number of rooms and number of bathrooms, let's say there is always an attached bath to a room, then, you know, including number of rooms and number of bathrooms as separate covariates is sort of redundancy. So the point of this assumption is there is no redundancy in the data. Second thing it says is that, you know, ultimately it means rank of this matrix X is equal to k, implies that n is greater than or equal to k. That is to say that we have at least as much data as as we have variables. Okay, remember, to each k is attached a coefficient beta. So that's what we are saying, that, you know, to each variable there is at least one data point that corresponds to more than that. That makes sense, right? We can't have 10 data points and 10 covariates. That's going to be a very difficult situation. Okay. Now this relates to also also to what is called as a dummy variable trap. I'm going to leave you with this interesting term, dummy variable trap, and I'm going to give you a home assignment to study this from the book on econometric analysis by Woolridge, right? You can say Woolridge's Advanced Econometric Analysis. You must read the first 2 chapters, and if you read them, you will figure out what is dummy variable trap. You should find this term and study it from the book. This will also give you a very nice review of this, what we have covered in this, in this class till now. Quickly, the 5th assumption of a regression model is that X, this matrix X, contains factors that are, non-stochastic. That is to say, when we say that the number of rooms is 3, we don't mean 3 with some error. We say it's 3, right? It's a degenerate, matrix. Assumption 6 is that the error term is normally distributed. That is to say that UI is normal with a mean and a variance for all I, and these are all IID. Okay. If we look at our assumptions, assumption 1, assumption 2, assumption 3 and assumption 6 will imply that UI is IID normal 0 sigma squared for all I. Okay, this is a crucial assumption. Now finally, I want to just, in this recap, I want to talk about what is called as the least squares estimator. The least squares estimator. I've been saying that ultimately we want to be able to, estimate these beta zeros and beta ones and so on and so forth. So I have a model, a truth representation of the truth given as the following. Let us say I have this representation of the truth that I want to explain yi based on a model equals beta 0 plus beta 1 x1i plus beta 2 x2i till ui. Okay. Now I have data on these things, right? I have data on 1, 2, all the way till n. I have n values and I want to figure out what is the database representation, right, of, so we need to find or estimate is beta 0 hat, beta 1 hat and beta 2 hat with n data points for both y, x1 and x2. We have n data points and the knowledge of above true model, right? So the true model is giving me what are the parameters to be estimated, and it is also giving me the specification that both x1 and x2 are entering as linear regressors, and there is a constant of ones, and there are 3 parameters, the model parameters, coefficient parameters, that is beta 0, beta 1 and beta 2 to be estimated. So least squares estimator, the algorithm is to minimize what is called as the sum of squared errors. So we take the errors at every instance of my data observation, we calculate the error and we minimize it. That is, we want to minimize yi minus beta 0 minus beta 1 x1i minus beta 2 x2i the whole squared. So I am conducting this minimization exercise while I choose beta 0, beta 1 and beta 2. It's an optimization problem. I will write my first order conditions, but ultimately this exercise will yield beta 0 hat least squares, beta 1 hat least squares and beta 2 hat least squares, right? The model representation, the prediction or the predicted value from model estimation is given as yi hat, which is nothing but beta 0 hat plus beta 1 hat x1I plus beta 2 hat x2I. So if I were to visualize this on a scatter plot, I have my x1I and yi. Of course, there is also x2I, which can be viewed in the third dimension, but I'm restricting myself to the cross-sectional representation, scatter plot representation of yi's and x1i's. Let's say I have my stylized scatter plot that I've been working with till now. Okay, and I am able to estimate a regression where this represents beta 0 hat and the slope of this line is beta 1 hat. Now, to every value of xi, x1i rather, I have a true value and a predicted value and another true value. Okay, so here is the prediction, which is yi hat, which is given as beta 0 hat plus beta 1 hat plus beta 2 hat x2i. Okay, and the truth is yi. There are two truth values here, yi1 and yi2, let's say. Then the model residual term, that is what this model could not explain, is the distance between the truth and the predicted value, that is yi minus yi hat is nothing but the value ui hat, right. Now you can represent ui hat values in this fashion. To each xi, we can have more than one ui hat. In fact, we have typically more than one ui hat value if we have a dense enough data set. Now, given very crucially, and this is the point where I'm going to end this review of the regression analysis, but then I am going to then articulate the departure from the typical traditional regression analysis to spatial regression analysis from this point that I'm going to make next. That is, given the assumptions A1 to A6, right, the 6 assumptions that we articulated today, we can say that beta 1 hat least squares is blue, right. Equivalently, we will also say beta 0 hat least squares is blue and beta 2 hat least squares is also blue. This idea of a blue estimator you should study from what is called as the Gauss-Markov theorem, again articulated very well in Woolridge's book. Otherwise also Gauss-Markov theorem is so popular that you can, we don't have time in this course to go over it, but any introductory econometrics course basically introduces the Gauss-Markov theorem. Okay, so by Gauss-Markov theorem, given assumptions A1 to A6, the beta hats that are arrived from the least squares algorithm are blue. What does blue mean? Well, blue means that they are best linear, unbiased estimators. Okay, they are a best guess of the truth. Okay, and when it means what it means by best, we will look at as we sort of walk through different parts of this course. What unbiased means that expectation of beta k hat least squares is exactly equal to the true beta k. Okay, so you have beta hat least squares is exactly equal to beta k, which is the truth. Remember, we are looking at the truth as well as we are looking at its estimate. The estimate is a function of data. Truth is just the model representation of the real world where yi can be linked with x1 and x2, right. Once we are given the data, we are practically somehow getting a representation of beta 1 and beta 2 and beta 0. Is it a good representation? Well, it is good given that we have these assumptions satisfied. And as soon as we depart from these assumptions in any way, that's where we are going to look at the spatial dependence. So spatial dependence is going to specifically interfere with, so spatial dependence will interfere with A2, which is the causal inference, perhaps the most crucial assumption, and A3, which is the assumption that the variance covariance matrix is a diagonal matrix, the off diagonal elements are 0, and all the diagonal elements are exactly the same. Spatial dependence will, will interfere with these two assumptions, and this is where we are going forward, we are going to first introduce spatial dependence or spatial regression as in the next lecture, and then using this recap, we are going to then depart and from or relax the two assumptions, that is A2 and A3, and then we are going to figure out how we can estimate these models even when there is spatial dependence and they interfere with the assumption of the least squared estimator, making it a not best linear unbiased estimator. So it will, with A2 it will introduce bias, spatial dependence will introduce bias, and with A3 it will interfere with it will interfere with the fact that the estimator is best or not. What we will see is that when A3 fails due to spatial dependence, we will have a better estimator. We will have something else that will be a better representation of the true estimator. Okay, so thank you very much for your attention. I understand that this recap could be a little bit fast moving for some people who have not seen regression analysis before. I highly encourage you go over these lectures again, this set of lectures 16 again, and read Woolridge's book. Read the introduction of regression analysis from that book. Even if you have seen regression analysis before, please read Woolridge's book. Okay, after that, I believe the upcoming lectures will become much more easier to understand conceptually. Okay, so thank you very much for your attention, and we will see you in lecture 17 next.